Good day, everyone. I hope you are all safe, secure, and healthy amidst this pandemic that we are facing right now. So, welcome to our sixth lecture on methods of integration with the topic outline on trigonometric substitutions, quadratic expressions, algebraic substitutions. So what is expected from you in this session is you'll be able to evaluate integrals involving algebraic functions, wherein you can use trigonometric substitutions to evaluate some problems, or you're able to evaluate integrals involving quadratic expressions, or simply pure algebraic substitutions. Let's start with the first outline on trigonometric substitution. Now, there are certain types of integrals involving algebraic expressions which can be evaluated when we transform them into a problem wherein it involves evaluation of trigonometric integrals. What I'm saying is, if certain integrals involve algebraic expressions, we can evaluate these integrals by transforming them into a problem of evaluating trigonometric integrals. Now, these transformations involve the trigonometric substitutions that are integrable and are as follows. Now, there are three cases wherein we can use trigonometric substitution to evaluate integrals involving algebraic expression. Case number one, it says, when the integrand contains the expression a squared minus u squared, we can use the substitution u is equal to a times sine theta. For case number two, it says, when the integrand contains the expression u squared plus a squared, use the substitution u is equal to a times tangent theta. And for case number three, when the integrand contains u squared minus a squared, use the substitution u is equal to a times secant theta. Now, for simplicity, we assume that theta in this trigonometric substitution is an acute angle. U is a differentiable function of x, and a is any number. Now let's have example number one. We are going to evaluate the integral of x dx divided by the square root of 4 minus x squared. Now, which do you think of the three cases is applicable in evaluating this integral? Now, by examination, we observe that the integrand contains the expression 4 minus x squared, which is of the form a squared minus u squared. Hence, we let a equals 2, or that is the square root of 4, the positive square root of 4, and we let u equals x. Therefore, x is equal to 2 sine theta. Okay? Or that is u is equal to a times sine theta. Why? Because our integrand contains the expression a squared minus u squared. Now we are going to derive x with respect to theta. And so the first derivative of x is 2 times cosine theta d theta. And given that x is equal to 2 sine theta, we can solve for sine theta in terms of x. And so we have sine theta is equal to x over 2. Now, since our first derivative of x, or our dx, contains the trigonometric function cosine theta, now we will be dealing with the trigonometric ratios, particularly on cosine theta. So from trigonometry, we all know that sine theta is the ratio of the opposite over hypotenuse. Okay? Sine theta is the ratio of the measure of the opposite over hypotenuse. Now, given this information, we will try to find the equivalent expression for cosine theta, since our dx contains the trigonometric function cosine theta. Now, from trigonometry again, cosine theta is the ratio of adjacent over hypotenuse. Again, cosine theta is the ratio of the measure of adjacent over hypotenuse. Now, given this right triangle here, we are going to solve first for the measure of the adjacent, so we can find the equivalent expression for cosine theta. Now, how are we going to solve or to find the value of the adjacent leg or the adjacent side? Now, we use the trigonometric ratio. It states that cosine theta is equal to adjacent over hypotenuse. Now, using Pythagorean theorem, we can solve for adjacent by using the measures of the opposite side and the measure of the hypotenuse. So solving for b, we let b our adjacent. B is equal to the square root of 2 raised to 2 minus x raised to 2. And so we get b is equal to the square root of 4 minus x squared. And so we have the equivalent expression for our cosine theta. Cosine theta is equal to the square root of 4 minus x squared all over 2. Now, simplifying this cosine theta, this equivalent expression for cosine theta, we have 2 cosine theta is equal to the square root of 4 minus x squared. Now, why do we cross multiply 2 to cosine theta? Remember that our dx is equal to the expression 2 cosine theta d theta. So we express this value of cosine theta into 2 cosine theta and find its equivalent expression. Now, given this information about x, about dx, and about 2 cosine theta, we can now evaluate the given integral. So the integral of x dx all over the square root of 4 minus x squared is equal to the integral of 2 sine theta times 2 cosine theta d theta divided by 2 cosine theta. Now, how did we use this information highlighted in evaluating the integral? We all know that the value of x is 2 sine theta, and so we substitute 2 sine theta to x. And we substitute 2 cosine theta d theta to dx. And the denominator, square root of 4 minus x squared, is now being replaced by 2 cosine theta. If you notice, we are substituting this information that we generated a while ago to evaluate the given integral. Now, simplifying the integrand or transforming the integrand, we eliminate 2 cosine theta, numerator 2 cosine theta, and the denominator 2 cosine theta. And all we left is 2, the integrand 2 sine theta d theta. Now, applying integral of the product, we have 2 times the integral of sine theta d theta. And we learned from our previous lecture on integrals of trigonometric functions, integral of sine theta is equal to negative cosine theta plus c. And so we have negative 2 times cosine theta plus c. And then we substitute that the equivalent expression for cosine theta, wherein cosine theta is equal to the square root of 4 minus x squared over 2. Simplifying this expression, we get the final answer. The integral of x dx over square root of 4 minus x squared is equal to negative square root of 4 minus x squared plus c. Now let's have example number 2. We are to evaluate the integral of dx over 4x squared plus 9. First thing to do is to examine the integrand. Which do you think of the 3 cases is applicable in evaluating this integral? We notice that the denominator of the integrand contains 4x squared plus 9, which is of the form u squared plus a squared. Hence, a is equal to 3, the positive square root of 9, and u is equal to 2x. Now we all know that when our integrand contains the expression u squared plus a squared, or can be represented in through the expression u squared plus a squared, we can use the trigonometric substitution, which is u is equal to a times tangent theta, where u is 2x and a is 3. And so we have 2x is equal to 3 times tangent theta. Solving for x, we have x is equal to 3/2 times tangent theta. Differentiating x with respect to theta, we get dx is equal to 3/2 times secant square theta d theta. Given that our x is equal to 3/2 times tangent theta, we can solve for tangent theta by expressing it as a function of x. And so we have tangent theta is equal to 2x over 3. From trigonometry, we know that tangent theta is the ratio of the measures of opposite side and adjacent side. So given a right triangle, given the measure of our theta, the opposite side measures 2x and the adjacent side measures 3. Now we will find or solve for the value of our secant theta. Now why solve for the value of secant theta? Remember, our dx, or the first derivative of x, involves a function, secant theta. Now applying Pythagorean theorem, we can solve for the value of the hypotenuse, given the measures of the opposite side and the adjacent side. So we have c is equal to the square root of 2x raised to 2 plus 3 raised to 2. Simplifying this, we have c, or the hypotenuse, is equal to the square root of 4x squared plus 9. So we have the equivalent expression for secant theta is equal to the square root of 4x squared plus 9 over the adjacent, which is 3. Then we perform cross multiplication. We have 3 secant theta is equal to the square root of 4x squared plus 9. Now why did we get 9 times secant square theta is equal to 4x squared plus 9? Simply, we square both sides of the equation. So we let 3 times secant theta square and square the right side of the equation. So we get 9 secant square theta is equal to 4x squared plus 9. Now we will use these two information that we have to evaluate the given integral. So we substitute the value of dx, which is 3/2 times secant square theta d theta. And substitute 9 secant square theta to the denominator of the integrand. So we have the integral of dx over 4x squared plus 9 is equal to the integral of 3/2 secant square theta d theta divided by 9 times secant square theta. Simplifying this, we can eliminate secant square theta. So, and we divide 3/2 by 9. And so we get 1/6. Now we have 1/6 times the integral of d theta. So we get 1/6 times theta plus c. Now what is the value of this theta? Now which of the information that we have is the value of theta? From our previous information, we know the tangent theta is equal to 2x over 3, or divided by 3. Now we can get the value of theta by getting the inverse tangent of both sides of the equation. So we multiply arctan, or the inverse of the tangent function, to both sides of the equation. And so we get theta is equal to arctan of 2x over 3. Substituting this value of theta, we have 1/6 times arctan of 2x over 3 plus c. Now I would like to introduce these other standard formulas, because these formulas are used frequently, and so I decided to emphasize them so you will be introduced to them and get familiarized with them. Later, we will use some of these theorems in solving or evaluating integrals. We have theorem 25 that states that the integral of du over u squared minus a squared is equal to 1 over 2a, or 2 times a, times the natural logarithm of the absolute value of u minus a divided by u plus a plus c. We also have theorem 26 that states that the integral of du divided by a squared minus u squared is equal to 1 over 2a times the natural logarithm of the absolute value of a plus u divided by a minus u plus c. Theorem 27 states that the integral of du divided by the square root of u squared plus a squared is simply equal to the natural logarithm of the absolute value of u plus the square root of u squared plus a squared plus c. Theorem 28 states that the integral of du divided by the square root of u squared minus a squared is equal to the natural logarithm of the absolute value of u plus the square root of u squared minus a squared plus c. We also have theorem 29 that states that the integral of the square root of a squared minus u squared du is equal to u over 2 times the square root of a squared minus u squared plus a raised to 2 over 2 times arcsine of u over a plus c. We also have theorem 30 that states that the integral of the square root of u squared plus a squared du is equal to u over 2 times the square root of u squared plus a squared over 2 times the natural logarithm of the absolute value of u plus the square root of u squared plus a squared plus c. And theorem 31 states that the integral of u squared minus a squared du is equal to u over 2 times the square root of u squared minus a squared plus a squared over 2 times the natural logarithm of the absolute value of u plus the square root of u squared minus a squared plus c. Now let's have integrands involving quadratic expressions. Those integrals that involve any of these forms fall under integrals involving quadratic expressions. The integral on the square root of f of x dx. We also have integral of dx over the square root of f of x, and the integral of dx over f of x, where f of x is a quadratic expression in x. Now, how are we going to evaluate this type of integrals that have in quadratic expressions? Now we use the process of completing the square. I hope everyone is familiar with this completing the square algorithm or completing the square method. But for the sake of those who cannot recall completing the square method, we have examples that will illustrate how completing the square is used. Recall that completing the square method transforms any quadratic expression into the sum or difference of two squares. Now, when a given quadratic expression in x is transformed to sum or difference of two squares, then it's possible to use the theorems that we discussed or I have presented a while ago. Let's have example number 1. We are to evaluate the integral of dx over 4x squared plus 12x plus 25. If you notice, our denominator is expressed as a quadratic expression, 4x squared plus 12x plus 25. By the way, the ability to see factorable quadratic functions is a must in this topic. Now we let our f of x, or the function of x, equal to 4x squared plus 12x plus 25. Now how are we going to apply completing the square method? Or can we apply completing the square method in factoring or in expressing this f of x into sum or difference of squares? Let's see. Now what did we do here? Simply, we express 25 as the sum of 9 and 16. And so we have this 4x squared plus 12x plus 9 plus 16. And what do you think is the purpose of doing this? Now we apply associativity rule in this part of the solution. We associate 4x squared plus 12x plus 9. But why? Why associate these first three terms? Because this 4x squared plus 12x plus 9 is a perfect square trinomial, and which can be expressed as 2x plus 3 raised to 2. And so we have the quantity 2x plus 3 raised to the power of 2 plus 16. Now we express already our f of x as a sum of two squares. So we transform our integrand into dx over the quantity 2x plus 3 raised to 2 plus 16, where u is equal to 2x plus 3, and a is the positive square root of 16, which is 4. Now differentiating u with respect to x, we get du is equal to 2 dx. And solving for dx in terms of du, we have dx is equal to 1/2 times du. Remember that this transformed integrand is of the form of theorem 23 that states that the integral of 1 over a squared plus u squared du is equal to 1 over a times arctan of u over a plus c. Now applying this theorem 23, we get 1/2 times the integral of 1 over u squared plus a squared du. We have 1/2 times, applying theorem 23, we have 1/2 times 1/4 arctan of 2x plus 3 over 4 plus c, where 4 is our a, 2x plus 3 is our u. Simplifying further, we get 1 over 8 times arctan of 2x plus 3 over 4 plus c. Let's have example number 2. Evaluate the integral of the square root of 5 minus 4x minus x squared dx. We let our f of x equals 5 minus 4x minus x squared. Then we associate x squared and the term 4x. So we have 5 minus x squared plus 4x. Now we apply completing the square method in expressing our f of x as a sum or difference of squares. But how did we apply completing the square method? Now in the given expression of f of x, our b, or the value of the numerical coefficient b, is 4. Now to apply completing the square method, we get half of this 4 and square it. And then add the result to 1 to the first square and to the second square. And so we have 5 plus half of 4 square minus x squared plus 4x plus half of 4 square. Again, how did we apply completing the square? First, identify or determine the value of the numerical coefficient b. And then get half of that numerical coefficient b and then square it. And then add the result to the first square and to the second square. Simplifying this, we have 9 minus the quantity x squared plus 4x plus 4. The second square is a perfect square trinomial. And so we can express it as a square of a binomial. So we have 9 minus the quantity x plus 2 square. Now we transform already our integrand. So we have the integral of the square root of 9 minus the quantity x plus 2 square dx, where u is equal to x plus 2 and a is the positive square root of 9, which is 3. Then we derive u with respect to x, and so we get du is equal to dx. Remember theorem 29 that states that the integral of the square root of a squared minus u squared du is equal to u over 2 times the square root of a squared minus u squared plus a squared over 2 times arc sine of u over a plus c. Now applying this theorem, we get the integral of the square root of a squared minus u squared du is equal to x plus 2 over 2 times the square root of 5 minus 4x minus x squared plus 9 halves times arc sine of x plus 2 over 3 plus c. Let's have example number 3. We have the integral of 2x plus 9 all over x squared plus 2x plus 5 dx. Take note, there are integrals in which we do not start by transforming the quadratic functions into sum or difference of two squares by using completing the square process. Instead, we examine it first if direct use substitution is applicable. Now in this case, we notice that the denominator of the integrand is equal to x squared plus 2x plus 5. If we let u equals this expression and we derive u, somehow we will arrive to a differentiated function that is expressed in the remaining term of the integrands. To make it clear, we let u equals x squared plus 2x plus 5. Deriving u, we get 2x plus 2 dx, which is somehow related to the remaining terms of the integrand, that is the numerator and the notation dx. However, the remaining term of the integrand after we use substitution is 2x plus 9. Now is 2x plus 2 equal to 2x plus 9? Definitely it's not. But we can do something to 2x plus 9 to make it equal to 2x plus 2. So we have the integral of the transformed expression of the numerator, which is 2x plus 2 plus 7 over x squared plus 2x plus 5 dx. But why express 9 as the sum of 2 and 7 and then apply associativity rule? Later, we'll know. Now we can express our integrand as the sum of two similar fractions. And so we get the integral of 2x plus 2 all over x squared plus 2x plus 5 dx plus the integral of 7 over x squared plus 2x plus 5 dx. We apply integral of sum or linearity principle. Now the first integral is of the form or follows the form or uses u substitution. Okay, where we let u is equal to x squared plus 2x plus 5 and differentiating u with respect to x, we get du is equal to 2x plus 2 dx. And this can be expressed as a logarithmic function, the integral of 1 over u du, plus, evaluating the second integral, we have 7 times the integral of 1 over the quantity x plus 1 square plus 4. How did we get the quantity x plus 1 square plus 4? Simply we apply completing the square method. We apply completing the square method to the quadratic expression x squared plus 2x plus 5. We expressed 5 as the sum of 1 and 4, and then associate 1 to the first two terms, x squared plus 2x. Then examining it, it's a perfect square trinomial, and therefore, it can be expressed as a square of a binomial. So we have the quantity x plus 1 square plus 4. For the integral of 1 over u du, we apply theorem 13, which was discussed already under integral of logarithmic functions. And use theorem 23 to evaluate the second integral. We can use theorem 23 that states that the integral of 1 over a squared plus u squared du is equal to 1 over a times arctan of u over a plus c. And so we get the final answer. The integral of 2x plus 9 over x squared plus 2x plus 5 dx is equal to the natural logarithm of x squared plus 2x plus 5 plus 7 halves times arctan of x plus 1 over 2 plus c.